with computer audio. Start video. Daniel's with us. Let's see who else we've got here. Okay, Tuesday, October 27th. Physics 2. And we've got Phoebe and Daniel so far. Hello.
Hi, I'm driving. I'm sorry.
Well, like I always say, be careful. No distractions. We don't want anything bad to happen to you. Okay, well, we just have the two students right now. Any comments or questions before we have our fun 3-hour Physics 2 class? Ooh, well, okay. It's darn near 5:30. I didn't bring my cell phone, but I don't guess I'll need it unless there's a problem and I have to call my IT person. Let's see, what about any homework here? Let's see where we are on the homework situation. Today's the 27th. I put your lab that you're going to be doing Thursday night on Blackboard, so you can, it's under content like always, and you can pull it up and study it. There's 3 equations there. We've had them before, but this time we're going to do it with the oscilloscope, so that'll be fun. Let's see what we got here. This is the 27th of October. You know what? That lab Thursday night will be lab number 9. Time marches on, lab number 9. Okay, now let's see. Your homework is homework assignment number 11. Let me write that down. Homework number 11. And it will be due the 30th, which I think is Friday. I don't know, let me look and see. Yep, that's Friday. And it is, now this is a handout problem. So you're going to have to go to content, I think. No, I think it's under homework. It's either under content or your homework. And there's a link, and if you click on it, up will come your homework. But it's not a problem out of your book. It's a problem that I've put on the link. It's a, how did I call it? I call it a, I forget what I called it. I call it a handout problem. Only I'm not handing it out. It's online. Back in the old days, I would hand them out. Remember those days where we passed out papers and things? It's on, you'll find it. Okay, well, let's get started with our work tonight unless anyone has a question. Let me see who's on board here. Oh, we've got Zach and Phoebe, Nicholas, and Daniel. Got a good bunch here. Anyone have a question before we begin? Well, okay. The first topic is going to be this equation here for the magnetic field for a short wire. And we've seen this before. I think I derived it. Yeah, I derived it. There it is. That's the magnetic field for a short wire. We derived it from the Biot-Savart law. So let's practice using it on a square loop. This is a fairly simple idea. We're going to take a square here. And we'll put some current in there. Let's say the current is going around this square loop clockwise. I'll just make up a current. Let's say it's 10 amperes. There, around and around she goes. 10 amperes. Now you could have multiple loops, like you could have 50. You could have 50 loops going around, but we'll just have the one. That's good enough. And what we're after here is the magnetic field smack dab in the center of the loop. Now, that magnetic field is either coming out of the board. If it's coming out of the board, you would write the magnetic field like that, like with a an arrowhead, you know, coming at you. Or it's going into the board, in which case you would write the magnetic field going into the board. You're sort of looking at the tail feathers of an arrow. And see, I've taught you guys well. You know exactly what that is, and I'm going to ask one of you. Zach, unmute and say hello, Zach, please.
I'm indisposed. Give me a second.
Oh, that's fine. I'll ask somebody else. I'll pick on you later. Stephen, unmute and say hello, please.
Hello. I
Yeah.
just signed in, so.
Oh, you just signed. Well, let me pay Nicholas. Nicholas, unmute and say hello, please, Nicholas.
Hey.
Hey, Nicholas. Current's going around this square current loop, and the magnetic field in the center is either going into or out of the board. You have a 50-50 chance of getting this right, Nicholas. What is it? In or out?
Mr. Griffin, I got it now. It's into. I just had to finish.
Okay, Zach, you're right. You're absolutely right. But now explain, Zach, how did you know?
Because the cross is on the board. When it's coming out, we put a dot.
I didn't quite understand it. Say that again, Zach.
Because we put an X in the circle instead of a dot.
Well, yeah, but Zach, I put a dot here a minute ago, and then I asked my class, well, which way is it, coming out or going in?
It's coming out.
Just a minute. Zach, you just said it was going in, and now you're saying it's coming out.
Well, a second ago you had an X. Now you have a dot.
Okay, I'm going to erase both of them. And Zach, I want you to tell me which way is it going. It can't be both.
Oh, you're asking about the general question. See, I was going.
Yeah. Now we understand. Which way is it going? Which way is the magnetic field going?
I think it's going into the board still
Yeah, it's going into the board. But now, do you know why? Why
because
is it?
direction of the field. I mean,
Yeah, why is it going into the board?
because of the direction of the current.
Yeah, but that's correct. But how does the direction of that current tell you that the magnetic field is into the board?
With the right hand rule.
Yeah, I
I mean,
yeah, okay. Well, here let me tell you the answer I wanted to hear, but I didn't quite hear it. You put your thumb along the current, and your fingers will tell you the direction of the magnetic field. See, the magnetic field on this side of the wire is coming out of the board, but the magnetic field on this side of the wire is going into the board. Now, if you put your thumb along the current here, do you see how your fingers go into the board? Now they come out of the board here, so there's a magnetic field out of the board here. Put your thumb along the current, fingers go into the board there, and they come out of the board here, so the magnetic field is out of the board. Everywhere out here, the magnetic field is out of the board, and everywhere in here, inside the loop, the magnetic field is into the board. That's the answer that I wanted to hear. Now, there's probably a nice picture in your book explaining this. But let me see if I can find it. I want you to understand this for sure. And let me dig around here. There's a picture of a guy's thumb. There it is. It's on page 545 in your book. There's a wire here. And the wire has current in it going this way. And then the person, they have their right hand. Zach was saying right hand rule. He's right. You put your thumb in the direction of the current. There's a picture of a guy with his thumb there. And you see how your fingers are coming out of the board on this side of the wire. And they're going into the board on that side of the wire. Put your thumb there. Right hand, got to be a right hand. Left hand won't work. See, they're coming out, and then they're going into. Well, that's the answer I wanted. And I'm glad we did that. And now we're going to find out exactly what that magnetic field is. But to get it, what you have to do is you have to draw a line here and here. There we go. And we need these distances. Let's suppose, those distances are, well, here, I'll just measure it. That's 15 centimeters. This distance is 0.15 meters. It's 15 centimeters. It's a square. So we have 0.15 meters. 0.15 meters, it's a square. Now we need this distance right here. Do you see that A right there? That's that A in the equation. And that would be, in this case, 0.075 meters. It'd be half of 15. So we've got the A, and hey, look, we've got the current. It's 10 amps. Now, what are these? Well, this theta 2 is right here. There's theta 2, and this is theta 1. Angles are always measured counterclockwise. So that theta 2, well, it's 45 degrees. Can you tell that? I mean, if this is a square, and that's 0.075, well, then this distance here is 0.075. And you could get that distance there, you know, it would just be, I don't think we need it, but if you wanted it, it's 0.075 squared plus 0.075 squared square root. There you go. See, these are what they call not equilateral, isosceles right triangles is the fancy name for those triangles. They're isosceles, which means they have two equal sides. And they're right triangles because there's a right angle right there. See it? And theta 2 is 45. Now theta 1 is negative 45 because, see, angles are, when you measure an angle this way, it's negative. Angles are supposed to be measured counterclockwise. You knew that. Okay, now look, here's an equation, and we're going to find the magnetic field of this short wire. We know everything. We know theta 2. We know theta 1. We know A. We know I. You know that mu sub 0. I'm going to shut up now, and I want you to find. Now, all we're doing now is just finding the magnetic field for this part of the square loop caused by that 15-centimeter wire. Okay, I'm going to be quiet. Get your calculators and find the magnetic field just due to that bottom wire. Go for it. Wonder if anybody's got that yet. How about my friend Stephen? Stephen, unmute and say hello, please, Stephen. Earth calling Stephen, come in.
all right, I thought I had it unmuted.
Oh, okay. Stephen,
I'm still
you're
still typing
working on
in.
it?
Give me just a second.
Yeah, okay, I'll wait. I think I've got it.
Okay. I'm getting a negative. That doesn't sound right. Okay, I'm showing negative 6.66 times 10 to the negative 7.
Something bad happened, Stephen.
Yeah. Oh, gotcha. I forgot to put in the current. That's still going to be a negative number, though.
How can you get a negative number? This turns out to be the sine of minus 45, which is negative, and you have a negative times a negative, which makes a positive. Everything's positive. You're not going to get a negative. How are you getting a negative?
So is what's in the parentheses sine theta 2 times negative sine theta 1?
And this is
Or is that a minus?
We're subtracting the sine of theta 1.
Oh, I mixed those up. There we go. Okay, 6.66 times 10 to the negative 6.
Again, I think something bad happened. Did you plug in A is 0.075?
Yep,
Did you plug in 10 amps for I?
I did.
Did you plug in mu sub 0 is 4 pi times 10 to the minus 7?
4 pi times. No, I used. Okay,
Do that.
I couldn't remember u sub 0. I thought it was the 8.77. That's a different number.
No, no, it's 4 pi times 10 to the minus 7. Tesla meters per amp is what it is. I'm glad we're doing this.
Okay, so I'll put that in, and I'm getting 9.543 times 10 to the negative 6.
I still think something bad happened. Maybe I should write it out. Here, let me write it out. Okay, we have 4 pi times 10 to the minus 7. We have 10. We have 4 pi times 0.075. Then we have the sine of 45 minus the sine of minus 45. Do it again, Stephen, and see what you get. Maybe I'm wrong. Maybe I should do it again. What'd you get this time?
That's exactly what I had in the first place.
Well, what I'm getting is 1.8856 times 10 to the minus 5 Teslas. That's what I'm getting. What am I doing wrong? Did anybody get what I got?
No, I got 2 point something. Hold on.
What about some of the rest of you?
I got the same thing.
You got that?
Yeah.
There's two.
1.88.
Yeah, there's two. Now, who am I talking to there?
Nick?
That's Nicholas?
Yeah.
So Nicholas and I agree. The rest of you do it again. Here, I'll do it one more time. Come on, guys, we got to get the same. We have to come out with the same answer here, or something's horribly wrong. We got to figure out what we're doing wrong here.
Yeah, I keep getting 2.269 times 10 to the negative 5th.
Okay, well, let's just break it down. Zach, let's do it step by step. Now, 4 pi times 10 to the minus 7 divided by 4 pi, that's just 1 times 10 to the minus 7. The 4 pi's cancel, right, Zach?
Okay.
Okay, and then you have 10 divided by 0.075. Now what this is, I know that by heart. I bet you do too. It's isn't it 0.7071 minus a negative 0.7071? Isn't that what the sine of 45 is? Yeah. And if you have a 7071.
Oh, I'm in radio mode. That's what's wrong. I'm in radio mode.
Hey, you just discovered something very worthwhile. You want to get the heck out of radian mode. That's good. See, this is not a wasted session. Now do that. Did you get this answer this time? I'll tell you what that is when you add those up. It's 1.414, isn't it? I bet you knew that by heart too.
All right, I got the same answer now.
You
I'm
get coming
good.
up with the same thing.
Yeah.
Well, great. Now, did I, let me multiply that and see if I, no, that's the answer, isn't it? The 1.414 has got to go down here. I'll get this right in a minute. Yeah. And if you put this in your calculator, you should get this answer. Let me try it. But I'm glad we went through that. Boy, Jove, that's exactly what you get. We did great. Now, we're not done yet, though, because, see, all we've got is the magnetic field of that wire. We got to get the other 4 wires. But since they're all the same distance, they all have the same current. And what you could do, I suppose, is you could draw these triangles like this. Can you see that the correct answer to the whole thing, all 4 wires, would just be this times 4? So you could make 4 of them. These all have the same A. They all have the same angles. See, here's your theta 2 and your theta 1. They're all the same. So if you take that times 4, here's what you'll get. You'll get 7.54 times 10 to the minus 5 Teslas for the whole thing. Did that make sense?
Yeah.
Yeah, great. Good. Now let's tell you what let's do. Let's do the magnetic field of a circular wire, okay? A circular wire. Here's what I'm going to do, guys. I'm going to make a circle. We're going to go around in here and make a circle. Making a circle. There. And we're going to find out what the magnetic field would be if you had 10 amps going around and around in this circle. See, here they go. There's your little current going around and around in that circle. Now we have an equation for that. It's called the magnetic field of a circular loop. And it's equal to mu sub O I over 2R. Now the R in this case would be, well, it'd be the 0.075. Can you see that? Well, let's do that. You know what mu sub O is. Do we have room there? Maybe. We're going to find the magnetic field. There's mu sub O. I is 10 amps. There's a 2 there, and the R is 0.075 meters. Put this in your calculators. Make sure it's in degree mode, not radian mode. And tell me what the magnetic field would be for that circular loop. I'll be quiet for a minute. Go for it. Well, let me see if, now, Phoebe, are you back out of your car where you're safe now?
I'm almost home. I'm not quite home yet. It takes me a while to get home.
We're not going to bother Phoebe. We're leaving her alone. I'm going to
Sorry.
go to Daniel. Daniel now. Daniel, unmute and say hello, please.
Hello.
Daniel, have you plugged in that equation for the circular, that one there, the circular, can you read it? It's kind of dark over there.
I think so.
What'd you get?
I got 8.378 times 10 to the negative 5.
That's what I got. I got 8.78. No, 8.378. Is that what you said? 8.378
Yeah.
times 10 to the minus 5 Teslas. Now let's compare that. With the square loop, we got 7 blah blah times 10 to the minus 5 Teslas. But with the circular loop, we got 8 point blah blah times 10 to the minus 5. You know what? The circular current loop gave us a little more magnetic field than the square one. Now let me ask somebody here. Let me ask Daniel. I got Daniel on the line here. Daniel, how come the circular current loop gives you a little bit more magnetic field than the square current loop? Daniel, how come?
Does it have anything to do with the size of it?
Yeah.
Is it slightly smaller than the overall
Yeah.
area? Slightly smaller.
Yeah, it's smaller. Yeah, it's smaller. Why would a smaller loop like that give you more a magnetic field, Daniel? How come?
Because it has less area, so it's more like condensed, I guess. I don't know how to word that.
Well, it sounds pretty good. That's not exactly what I wanted to hear. See, what I wanted to hear was every part of this circular loop is closer to the center. Well, there is part of the square loop right there that's the same distance to the center, but can you see that this part here is closer? Look how far away that is. And see, when you get farther away, you get smaller magnetic field. Does that make sense? The closer you are to the current, the bigger the magnetic field. That almost makes sense, doesn't it? Suppose you were miles away. Suppose you had current in a wire and you were miles away. What kind of magnetic field are you going to get? Well, not much, because you're so far away. How are you going to get a bigger magnetic field? You get closer. The closer you get, the bigger the magnetic field. Does that make sense, Daniel?
Yes.
Yeah, that's how come. That's how come. Okay, well, good. Let's do another one. I think we're going to have to do another one so that I'll feel confident you guys can do this. I don't have that warm, fuzzy feeling right at the moment. Now there's your homework, and you know it's not a homework problem in your book. You know, it's a problem that I've put on. It's on Blackboard, and you can push the link to it. So you can do that for homework, and it's due Friday. Okay, well, let's do a different one. All right, now this one's going to be, why don't we have, Why do we have 3 meters here and 4 meters here? And we'll have our 10 amps. Around and around she goes. We'll have, it's a square current loop, just like the other, well, no. It's a rectangular current loop. It's not square, is it? It's a 3 by 4. You think I did that pretty good with the 3 by 4? I think maybe it needs to be just a little bit more like that. There we go. I think that's more like it. Now what we want to do is we want to find the magnetic field smack dab in the center. Now let's see if you guys were listening before. We'll go to my friend Nicholas. Nicholas, is the magnet, there's going to be a magnetic field here in the dead center of this rectangular coil. Will it be going into the board or out of the board? You have a 50-50 chance on this, Nicholas. Which way is it going?
Into.
Yeah, good going. It's going into the board. And how do we know that, Nicholas?
'Cause
Explain.
When you grab the conductor,
You got it. That's it.
your fingers go into the board.
Which hand do you use? Your right hand or your left hand?
You're right.
Your right hand. You put your right hand along the current and your fingers, I can't, my hand won't do that one. But see your fingers going into the board. All right, now we're going to find out what we're just going to get this bottom wire here first. You need to draw this here and this here. There we go. Now we need this distance here. Now this is A. Remember how the equation goes? It goes like this. Come on now. There we go. And we all know and love that equation for a short wire. There it is. Oops, this is wrong. There, now at least I got the equation right. Okay, now this distance here, well, we need all these values. Can you read my writing? That's supposed to say 10 amperes. What's a little a? What is this little a right here? Looks like 1.5 meters to me. And what's the current? Well, the current is 10 amps, you know. Now we need this theta 2. Here's theta 2. And here's theta 1. What's theta 2? See, if we could only get these angles, we could do this. We got the current, we know the A. Yeah. Now we're only going to get the contribution of this bottom wire, but that's a start. Now let me ask one of my excellent students here. Well, we only have 5 of you wonderful students. Let's pick on Daniel again. Daniel, what is that theta 2?
I'd have to probably do math real quick. Hold on. If it's not 45, 45 would be my easy
No,
guess,
good-
but I'd have to do math.
Good going, Daniel. It's not 45. How would you get it?
Take the cosine of
Yeah,
2 over 1.5. Hold on, I'm getting it.
that might work.
Wait.
He's got the right idea. I don't know if that's right what he just said, but
No, I had it backwards. Cosine 1.5 over 2. I'm getting 41.41 degrees.
oh, that's not right.
And I don't know.
Daniel, you had the right idea, but you don't want the cosine. You want the tangent of theta 2 is 2 over 1.5. It's not the cosine. See, the cosine, you would have to have this
Yeah, I
hypotenuse.
see it now. Yeah, my bad.
Isn't this good?
I was looking at the wrong line.
Oh, this is good stuff here, Daniel. We got to know the difference between cosine and tangent. Okay, what do you get for the theta 2?
Okay, 53.13.
Yeah, that's more like it. Theta 2 is 53.13, I think. Let me try it. Yeah, it's 53.13. Now, guys, I want you to memorize this 3, 4, 5 triangle. You see that's 3 and that's 4. We have a 3, 4, 5 triangle. This angle down here in the bottom is 3687. And these angles here are 5313. This little angle here is 3687. It's a 3, 4, 5 triangle. Now, this is a 2, 1.5, 2.5 triangle, but here, let me draw it separate for you. It's a 2, 1.5, 2.5. May not look like a 3, 4, 5 triangle, but see, if you doubled it, if you blew it up, you know what you'd have? You'd have a 4 and a 3 and a 5, wouldn't you? See, if you made this twice as big, 2 times 2 is 4, 2 times 1.5 is 3, 2 times 2.5 is 5. You've got a bunch of 3, 4, 5 triangles in there. And I want you to memorize that if you have a 3, 4, 5 triangle, then that is the number of degrees in them. Just memorize it. I mean, you can stop and do it with tangents or cosines. See, you could have used the cosine. Look here. The cosine of theta 2 would be the 1.5, but you'd have to divide by the 2.5. See, all the way from here to here is 5, but from here to here is 2.5. Do that in your calculator and tell me if theta 2 comes out to be 5313. I pushed the wrong button. Take 1.5, divide by 2.5, and hit the arc cosine button. And boy, Joe, you get 5313. It's time you guys memorize that. I'll tell you what, instructors love to give exams that have 3, 4, 5 triangles on them. I don't know what it is that they're in love with the 3, 4, 5 triangle, but you might as well be familiar with it and recognize it. Look, 3 meters, 4 meters. If you went from corner to corner, if that's 3 and that's 4, well, that would be 5 meters from corner to corner. And so halfway would be half of 5. It's just 2.5. Memorize it. I think I've told my classes before, get your ruler out and make some cookies. Make some 3, 4, 5 triangles. You can make them 4 inches by 3 inches by 5 inches. Roll them out with a rolling pin. Put a little butter and jelly or whatever you want to on them. Put them in the oven. Cook them. I want you to internalize the 3, 4, 5 triangle. After they're cooked, eat them. That should internalize the 3, 4, 5 if you eat the cookie, right? Maybe crazy, but I want you to really have a handle on that. Okay, now we're gonna plug all these in. We know A, it's 1.5. We know the current is 10. We know theta 2 is 5313. Theta 1 is negative 5313. We know everything. Look, we know theta 2, we know theta 1, we know A, we know I, we know everything. I want you to find the magnetic field of just that bottom wire. Go for it. I'm going to do it. You do it. Let's see what we get. Well, I did all that and I got an answer. I wonder if anybody got what I got. Let me go to my friend Zach again. Zach, did you plug in all these? What'd you get?
7.5398 times 10 to the negative 6.
Well, that's not what I got, Zach. It's kind of close. You're kind of close. You're doing something right. Either that or I did something wrong. But you need to look this up. The sine of 5313, that turns out to be 0.8, doesn't it? The sine of 5313.
So
Yeah.
what did you earlier?
Turns out to be 0.8. And then you subtract. Now the sine of negative 5313. See, this one's going this way. That's negative. That turns out to be a negative 0.8. So 0.8 subtract a negative 0.8 is 1.6. So here's what we've got. We might have to do these all night till we start to get it right. We've got 4 pi, which cancels, the 4 pi is canceled, but you still have 10 to the minus 7, and you have the 10 amps, and you have the 1.5, and 0.8 plus 0.8 is 1.6. Okay, do that and tell me what you get. This might be what Zach got. What did you get again, Zach?
7.5398.
No, I'm not getting that. put this in your calculator and tell me what you get.
I'm not completely following exactly what we're doing, but I did the math there, and it's 1.067 times 10 to the negative 6.
Yeah, that's what I got. It's exactly what I got. I got 1.0, a whole bunch of sixes, times 10 to the minus 6 Tesla.
I forgot my pi.
Ah, he forgot the pi. See, this thing here is 4 pi times 10 to the minus 7. Don't forget the pi. Okay. Anybody else getting that? I need another uh-huh.
Uh-huh.
Yeah, there's one. There's one. Now we could do this same one for this one here. It has the same A. A is 1.5 for this one, and it's 1.5 for that one. When you plug in that one, the same current. The angles here. See, this would be the theta 2 and the theta 1. It would help if you just kind of turn the thing upside down. Can you see that these two wires here give you the same magnetic field? So you're going to have two of these. We'll add up the other one here in a minute. But so far, we're going to take that and we're going to add that. But now we haven't done these wires here yet. Let's do those wires. And then we'll do all four. Here we go. I need some room here. Okay, now this time, put your value of A here. Now A is, in this case, is 2 meters. So it's halfway across the 4 there. But now these angles here are different. Here's your theta 2, and here's your theta 1. What is that? What is that angle theta 2 right there? What is it? It's different than the theta 2 here, isn't it? See, that theta 2 there is the same angle that you have down here. What is that angle? Anybody know?
36.87.
Yeah, that's it. That's it. Good going. Here, let me write this for you. Theta 2. We're doing this wire right here, right now. That's what we're trying to do. Theta 2 is 36.87 degrees. Theta 1 is negative 36.87 degrees because, see, you'd have to go this way. Counterclockwise. See, or no. Yeah, no, clockwise. Yeah, that's right. See, counterclockwise is plus. You guys know the drill. That way, counterclockwise is plus, and clockwise, when you measure angles, is negative. Okay, good. So we got theta 2, we got theta 1, and we know little a, it's 2 meters. We know I, it's 10 amperes. So we know everything in the equation. And we're going to solve it. Plug all that in, and let's see if we can get several of us with the same answer. Here we go. We're going to plug in these numbers in this equation. On your mark, get set, go. Well, I got an answer. Did anybody get 0.6 times 10 to the minus 6 Teslas for the magnetic field due to this wire right here? Did anybody get that?
I got 6 times 10 to the negative 7, but when
That's
it
the
comes out to the same, that's just the
that's
same.
the
That's
same
just what my
thing as-
calculator's doing.
6 times 10 to the minus 7, that's the same thing as 0.6 times 10 to the minus 6, isn't it? Same thing. Now, when you do this wire here, we could go through all the steps and get that wire there, but it's going to be the same as that wire there. Both of these wires contribute the same amount. Now, if you want the total, to get the total magnetic field for this circular current loop, you got to add these babies up. Okay, I'm going to add them up. Here goes. I'm adding everything up now. We think that that rectangular current loop gives you a magnetic field in the center of 3 times 10 to the minus 6 Teslas. Now I got a question for you. These wires here, both of them give you the same answer, the 0.6 times 10 to the minus 6. These wires here, they give you the same answer, but look, it's bigger. It's 1.066 times 10 to the minus 6. How come those wires there give you a bigger magnetic field, and these wires here give you a smaller magnetic field? Let me ask one of my superb students. Phoebe, are you back in a safe spot now?
Yes, I am.
Phoebe, I want you to think and tell me how come that these vertical wires give me a smaller magnetic field and these horizontal wires give me a bigger magnetic field. Why is that, Phoebe?
I want to say it's because they're of a smaller length, but I feel like that's not right.
No, that's good.
That's all I've got. I'm sorry.
There's actually 2
I feel like
reasons. There's two reasons.
associated with that, there's going to be a difference in current, but I'm kind of stumped past there.
The current is 10 amps everywhere. There's no
Right, 10 amps, but it's over 10 amps over 3 meters versus 10 amps over 4 meters.
Ah, yes. Very good. Very good. These vertical wires are shorter, right? It would kind of make sense that because they're shorter, you would get a smaller magnetic field. That makes sense. But what's the other reason?
I'm stumped past that. I don't know other than that.
Well, I like that answer. These wires are shorter, and so they won't give you as much magnetic field because they're shorter. These wires are longer. Look, they're longer. They're 4 meters long. Makes sense that they would give you more magnetic field. But there's another very good reason. What is it? It's the same reason we had the last time. What is it? Let me pick on my friend here. Daniel, there's another reason why these magnetic fields are smaller than these magnetic fields. What's that?
It's because of the value of A.
That's it. That's it. There, it's farther.
Oh, I didn't even see that. Okay.
It's farther away. See, that's 2 meters, right? This here's only 1.5 meters. They're closer. Remember, if you get closer, the magnetic field is going to be bigger. If you go out a few miles away, you don't get much magnetic field. It decreases as you get far and farther away. There's two good reasons, two very good reasons. Okay, well, great. That was kind of fun. We probably should do some more until I get a totally good, warm, fuzzy feeling about this. Now let's do one more. We'll do one more. We'll go back to the square here. Now this time, just for something different, we'll have the current going this way. We can still have 10 amps, that'd be all right. But the current is going to be 10 amperes going around counterclockwise, right? And there it goes. And let's see how long these are. These are 12. No, they're 11 centimeters. They're 11 centimeters. It's a square. They're 11 centimeters. Everything's 11 centimeters. It's a square. Now we're going to find the magnetic field here in the center. Will it be coming out or will it be going in? I bet you know. I bet you know. We'll pick on my friend Zach. Zach, will this magnetic field here in the center be coming out or will it be going in?
According to which wire?
Well, they all are going to make it do the same. All four wires will make it do the
It's
same
coming out.
thing. You got it. Boy, Jove. Now here's how you draw a vector coming out of the board. You're looking at the tip of an arrow. And Zach, how do you explain why it's going out?
Because of the right hand rule, and you put your thumb in the
He's
current.
got it. It's the right hand rule. Now, I'm going to shut up for 2 minutes, and we have the equation. It goes like this. And I'm going to shut up, and I'm going to see if you can figure out the magnetic field of that square. We know everything there is to know, I think. We got the current and the dimensions. Okay, you got 2 minutes. See if you can do it. Go for it. Well, I don't know if I gave you enough time, but let's go to my friend. I'm always picking on Stephen for some reason. Stephen, did I give you enough time to figure what that magnetic field is there in the center of that?
I think so. 1.0285 times 10 to the negative 7.
You know, that's a funny thing, Stephen. I got the same 1.028 blah, 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 but I got a different exponent. I wonder what I did wrong. Let me write it out here.
I got 10 to the negative 6.
Well, I didn't get that either exactly. And we know that's 10 amps, right? Here, let's do this properly. Let's put in the units.
I forgot the current when I put it in the calculator.
Ah, well, we'll do it again. Here, I'm going to put in the units. This is what you're supposed to do instead of being lazy and leaving the units out. Now that A business, I think, is 0.055. Did I do that right? 0.055 meters? Yeah, I think that's right. See that little distance there? That's 0.055 meters, isn't it? And then you have to go the sign, and this, we're back to
That's
the
what I did wrong. I
I'm
found
sorry?
my mistake. I said I found my mistake. I
Oh,
had that number wrong, so that would make it off by a power.
okay. Well, now there's your numbers. But now don't forget, when you get all through, don't you have to multiply the whole dang thing by 4? Did you guys do that?
Yes.
Yeah. Okay, well, I got what I think is the answer. Let me do it again to be sure. And then I'll ask you. Let me see here. Okay, I think I have the answer. Go ahead. I think Phoebe's got an answer. What'd you get, Phoebe?
Oh, I'm sorry. I didn't actually correct my calculation, so I just
Okay.
made a note to fix it.
Well, that's okay. Take your time. What about my friend Stephen? Do you have that yet, Stephen?
1.0285 times 10 to the negative 4.
That's what I got. Now I got 1.0284, but let's don't fight over it.
I got what Steven got, so yeah, same thing.
Yeah, I think we're pretty happy about that. Now the units, can you see that the meters cancel, the amperes cancel, and you're left with Teslas? You have to multiply by 4 because there's 4 wires and the calculation is the same for all of them. Now, to reference that to the Earth's magnetic field, the magnetic field of the Earth is about, kind of do a little squiggle there. That means kind of, about, sort of. It's 1 times 10 to the minus 5 Teslas. So this is 10 times as big as the Earth's magnetic field. And it would be easy to make a loop like that. That would be easy. No problem. We could do that in the lab, easy. In fact, we can make much more powerful by making, instead of just one loop, we can make a dozen loops or 100 loops, right? Get some wire and go around and around, and we can get a magnetic field much bigger than the Earth's magnetic field. Even this one's 10 times the Earth. You might ask yourself, well, what causes the Earth's magnetic field? Well, inside the Earth, there's this stuff called magma. It comes out and it turns into lava with the volcanoes, right? And it's melted rock. It's red hot rock. Well, way down in the middle of the Earth, this stuff is moving, and if it moves in a semicircular path like this, it causes a magnetic field, just like that current in that wire. That's where the magnetic field of the Earth is coming from. And what's interesting is it can change. It doesn't just stay constant all the time. It can change maybe the angle a little bit. And so the North Magnetic Pole can move. It doesn't stay exactly in the same spot. It moves. Not only that, but it can change in its magnitude. Because if it maybe slows down a rotation, you'll get, that would be like having a smaller current. And you'll get a smaller magnetic field. And in fact,
Man, I don't know what's going on, but I still get 2.57 for this answer. I'm not getting this one that
well,
y'all
here, let
get.
me do it. Thank you so much.
That's what I got too whenever I did it.
Well, maybe we're wrong. I'm going to do this again here now. Now, what we got this. The problem is probably in here. See, the sine of 45 is 0.7071. And the sine of minus 40.
I see what's going on now. I did not. You had the full answer written down. I was getting the answer right before you multiplied it times 4.
Oh, okay. We'll multiply that by.
I was about to say I literally just saw that too. Never mind.
Yep. All right, I'm good.
So everybody, you guys are okay then? All right. Well, that's good. Excellent. I'm pretty happy with all that. Okay, well, we're going to move on now, unless somebody has a comment or question. All right. Well, we talked about short wires now. I'll tell you what. Let's do the circular current loop one last time. Now, see, we could put a circular current loop around the outside here. Let's do that. That'd be fun. Oops. Yeah, here we go. You see, I could make a circular current loop going around and around like that. And I can tell you what the radius would be. Well, we'll have to do a little math to get it. See, the radius of that would be, well, wouldn't you have to go 0.055 meters squared plus 0.055 meters squared, square root, in order to get that diagonal and the radius of that circle? Wouldn't you have to do that? That makes sense? Let me do it. Here goes. 0.055. I'm coming up with the radius of this circular loop is 0.07778 meters. Okay? Now what we're going to do is we're going to find the magnetic field of that circular loop. Now we have it. We have it for the square loop. Here it is. That's the answer. But let's see what it is using the equation for a circular loop. Remember that equation? It goes like this. This is the equation for a circular loop. And we figured out the R is point, that's R. That's the radius of our circular loop. And you know I, it's 10 amps. We're going to have 10 amps in the circular loop. Go ahead, I'll shut up. I want you to find that for me. Go. All right, let's see. I'll pick on one of my very best students here. Daniel, unmute and say hello, please, Daniel.
Hello. Give me 2 seconds. I punched it in wrong.
Okay, punch it in right.
Okay, I got 3.889 times 10 to the negative 8.
That's not what I got. Here, I'll write it out for you. This number is 4 pi times 10 to the minus 7. This here is 10 amps. That's a 2, and that's a 0.07778. Do it again, Daniel.
Okay, I got 4.887 times 10 to the negative 7.
That's not what I got. I guess we need to just do it step by step.
Get the
See,
eight.
on the first one, I left out 4 pi. So my
Okay.
math was probably just wrong on that one.
Did you
Yeah.
get the 8.078 times 10 to the negative 5th?
Yeah,
Times
that's what I got. I'm getting 8.078 times 10 to the minus 5th Teslas. Daniel, I want you to get that. I won't be happy until I hear Daniel tell me he's got that. You got to figure out what you're doing wrong here.
We might be here for a while.
I might be here for a while. Is that what he said?
Yes. I don't know. Every time I'm punching in exactly how it, how you wrote it out, because that's how I wrote it out. But I'm still just getting, every time I punch it in, I'm getting 4.887 times 10 to the negative 7th. I have a lot of issues with my calculator as far as like exponents and division.
And you divide it by point.
The calculator doesn't follow the conventions like when you write it down. You got to put parentheses in around the numerator, and then put parentheses around the denominator if you want to put it all in.
Yeah, you're right. That's what it was. I got it now.
You figured out what you were doing wrong.
Yeah. What
Good.
Nicholas just said helped me a lot. I got it now.
Good deal. I find that students can teach other students better than instructors can teach students. I've discovered that. Okay, now I want to show you something here. That number there could be written as 0.8078 times 10 to the minus 4 Teslas, which is smaller. Let me get rid of that. Which is smaller than 1.02 something times 10 to the minus 4. In other words, the magnetic field of this circular loop is smaller can you see that 0.8 times 10 to the minus 4 is smaller than 1 point blah blah times 10 to the minus 4? Now my question to you, now here's, let's see if Daniel can get this one for me and make me feel good. Daniel, how come the magnetic field for this circular loop is smaller than the magnetic field for the square root? Not loop, loop. How come the circular loop gives you a smaller answer? See, this is the square loop here. Let me draw a little square on there. There you go. How come the square loop gives you a bigger magnetic field, Daniel?
Because it's smaller and it's closer to the center.
That's it. By Jove, he's got it. The wires are closer to the magnetic field is going to be bigger because these wires are closer in the square, and the wire is farther away for the circular loop. Does that make sense to y'all? A little Southern talk there. Y'all get that? Okay, well, great. That was fun.
I get that, but does it also have anything to do with the surface area of the loop?
No, it's got nothing to do with the surface area of the loop. I think it has to do with the distance of the loop to wherever you're measuring the magnetic field. I don't think it's the surface area. It might be. Now, who was that? Was that Nicholas?
No, that was Stephen.
That was Stephen. Stephen, you might have something there, but I'm going to have to think about it. I don't know everything. But we're going to move on. That was loads of fun, but we're going to move on. The next topic is toroids. Let's talk about toroids, and then we'll take a little 10-minute break here. Now, a toroid, what that is it's kind of like a solenoid. Now, you know what a solenoid is. It's a bunch of wires wrapped in a, like that. Only the thing is with a toroid, what they do is they come around. It's kind of like a slinky. You guys ever played with slinkies when you were a kid? Well, you can kind of bend them like this. Now you're going to have to connect this to a battery, a plus and a minus. And what happens is you get a current, but they call this thing a toroid. And depending on how the current is going, if this is plus, and you have a current going like that, and it goes around and round and round and round, and of course the current would be finally coming out like that, going to the negative of the battery. Then we can figure the magnetic field by using the right-hand rule. And you'll discover there'll be a magnetic field throughout the inside of the toroid, like that. You could easily make one of these. You just need some wire and a battery. And I've never actually done it, but I thought of a kind of a fun project to get one of those Hot Wheels tracks and put it inside here and get your little Hot Wheels car. Here's your little Hot Wheels car, and glue a magnet on it. If you have a north-south magnet, that little car will follow this magnetic field and will just go around and round and round inside the toroid. Now, what we're going to do is we're going to come up with a magnetic field of the toroid. And the way we're going to do it is with Ampere's law. Ampere's law goes like this. We've had it before, but I think maybe it's good to mention it again. And it goes like this. And this magnetic field is constant throughout your inside of your toroid, so you could pull it out of your integral, and what you'll have is just the integration of the distance around your toroid, and that's just the circumference. The distance around there, let's call this the radius r, shall we? And so what the circumference is 2 pi r. And we'll do a little algebra step here, and we'll have our magnetic field for a toroid. Now let me show you that in the book, and we'll see if we got that right. That was pretty easy using Ampere's law. Let's see now, which chapter are we? Are we in chapter 11? No, we're in chapter 12. And I'm going to look up the magnetic field of a toroid now. And here it is on page can't find, here we go. It's on page 565. Now here's where I got it wrong. This is not right. This current here is the current in Ampere's law that penetrates your Amperian path. You have to have an Amperian path. Well, here's our Amperian path. We'll just pick this circumference here. And can you see that this wire here has current in it, and it's coming through here, and it penetrates your Amperian path. And then so does this one. So does each one of them. So what you have to do is you have to multiply this by the number of turns in your toroid. And now we've got it. We've got our magnetic field of a toroid. Now let's see what they said it was. This is on page 565. And the way they write it is the magnetic field of a toroid is mu sub O Ni over 2 pi r. There you have it. Yep, we got it right. We used Ampere's law, and we found the magnetic field for that toroid. Okay, well let's just do a quick calculation on that. Suppose you had, I don't know what that looks like to you guys. 1, 2, 3, 4, 5, 6. That's probably about 50 turns there. Suppose you had a toroid with 50 turns and a radius of, hang on a minute here, I'll measure this. It looks like about 8 centimeters. So the radius is 0.08 meters. You've got a toroid. It's got 50 turns. That's dimensionless now. That's just the number of turns. It's not in meters or anything. It's just 50 turns. And you've got the R. Now I use the big R. Oh, well, that's okay. I used a big R. They used a little r. Same thing. We've got the R. We've got the number of turns. Now the current. Now what have we been doing? 10 amps on everything? Let's just go with the 10 amps. So we'll have a current of 10 amperes in our toroid. So now do we know everything? Let's see. We know the current. We know the number of turns. Yeah. All right. I'm going to shut up, and I want you to find the magnetic field inside that toroid. Let's see if we can get the same answer this time. We've been getting different answers all night, and that's starting to bug me. I'd like for everybody to be able to get the same answer. Not that I don't make mistakes too. Go for it. Find the magnetic field of that toroid. Well, I got a magnetic field. I just wonder, let me go to some of my wonderful students here. Zach, do you have the magnetic field inside that toroid?
0.00125.
That's what I got. Yay. 0.00125 Teslas. It's exactly what I got. I feel good. And with that, we're going to take a 10-minute break. I'm going to go see what's in the refrigerator. I'll be back. In 10 minutes, I'll be back. So go stretch. Go stretch, and we'll be back. Okay. Ah. Well, I think it's about time to get back to work here. Let's do a problem out of the book. Let me make some room here. Now, the problem I want to do is problem 1257. 1257. Let me find it. Twelve 57. A toroid with a square cross section 3 centimeters by 3 centimeters has an inner radius of 25 centimeters. In other words, they're not making it out of circles, they're making it out of squares. Kind of hard for me to draw that. But they're just a whole bunch of squares. I think I'm going to give up trying to draw it. But you get the picture. It's going to go around in a big circle. Same idea. Connected up to a battery. It's just that instead of being circles, these are all going to be squares. Okay, you got the picture. And the radius is, you got 500 turns of wire. So N is 500. And they're 3 by 3 centimeters, has an inner radius of 25 centimeters. So this would be 0.25 meters. And these things are 3 centimeters, what, 0.03 meters? I guess technically, the radius would be the 0.25 meters plus half of that, which is 0.01. That's my guess. It has a current of 2 amperes. And they want to know the magnetic field here. Well, it kind of depends on which way the current is moving. But if it was going like it was on this circular coil, then you would have a magnetic field going around in a circle equal to, oh gee, I erased the equation. Is it 2 pi I, wait a minute, let me go back and find it. I lost it. I can't remember everything. It's mu sub O Ni over 2 pi r. Now we know what mu sub O is, and we know what N is. N is 500, I is 2 meters. They're using a little r in their equation. But I think the little r would be this here, if that makes any sense, which would be how much? 0.265? Looks right to me. Okay, I'm going to shut up. I'm going to let you plug that in and find the magnetic field of that toroid. On your mark, get set, go.
Could you explain how you did R again? I missed that part.
Yeah.
Sorry.
Now, I don't know if this is what they wanted us to do. But see, what they gave us was just the distance to the beginning of these loops. And what we've got to have is the distance all the way to the center of the loops. See, these are little squares. They're 3 centimeters on a side. And over here you have a distance of 25 centimeters. But I think we've got to get the distance from here to the center, which would be the 25 plus the 1.5. Does that make sense, Zach?
Yeah.
I think that's what they wanted us to do. Well, we'll find out here in a minute. Plug all that in and let's see what we get. I'm getting an answer of 7.547 times 10 to the minus 4 Teslas. Anybody getting that?
I did.
Yay! Let's see if that's what they wanted. I don't know if we did it right. This is 1257. I'm gonna look up the answer. Here we go. Trying to find 1257. Now what they said was the answer book says the magnetic field is 0.0008. Now what did we say it was? Well, I think if you rounded it off, we'd be okay. See, that's pretty sloppy, you know what? I think our answer is the same as theirs. See, what that is 8 times 10 to the minus 4. And we're getting 7.5 times 10 to the minus 4. I think we're okay. Let's move on. Now you know about toroids. Okay, let's do this one.
They didn't add the. They didn't go to the middle point.
Oh, they didn't? Did
No,
they?
I just put it in, and that's what that 8 exactly is what I got.
Oh, okay. Well, maybe I read it wrong. Just a second here. Okay. I think it's a matter of interpretation of what they mean by the inner radius. But we came pretty close. I'm not going to worry about it right now. Let's do a different one. Now this is problem 1259. Let me make some room here. But thank you for that contribution. This is problem 1259. And let me find it. 1259. Okay. Now, they're talking here about something called susceptibility. And I didn't explain that to you guys. But let me explain it to you now. Now is as good a time as any. There are 3 kinds of magnetic materials. There's diamagnetic materials on page 568. We'll get to our problem here in just a minute, but on page 568, there's diamagnetic materials. And it turns out that all materials are diamagnetic. All materials are, including human bodies. In fact, they did an experiment with a frog. It turns out that if you put a frog, because it's mostly water, water is diamagnetic along with everything else. If you put a frog in a magnetic field, the frog will levitate. You can levitate a frog because the molecules in the frog, made of water, will create a magnetic field opposing the external magnetic field. So like if you have a magnetic field doing this, and here's your frog. I won't attempt to draw a frog. Yes, I will. Maybe I should have not done biology, huh? That ain't the greatest frog in the world. But see, what happens is it creates an opposing magnetic field. Diamagnetic materials create an opposing magnetic field. It has to do with the unpaired electrons in their atoms. And it's an interesting experiment. I don't know, I guess you could Google it and look up the diamagnetic magnetic field to levitate a frog. I guess type that in and it'll tell you all about it. All materials are diamagnetic, but it's a very weak effect. Now there's another weak effect called paramagnetic materials. And there are many substances that are paramagnetic. In fact, there's a list here in your book. Aluminum, calcium, chromium, magnesium, oxygen gas, a lot of metals are paramagnetic. Now what that means is you put them in a magnetic field and their magnetic field will align. It won't oppose like the frog. They will align. In fact, it will increase in the material. Like if it's magnesium, the magnetic field will be bigger than just the external field. And the amount that it will be bigger is this thing called the susceptibility. And they use a lowercase Greek letter chi, C-H-I, for susceptibility. And here's the equation. This is an induced magnetic field. It's equal to chi times your external magnetic field. The symbol they use here, I don't know why they picked that. But see, you could have a solenoid or a toroid that was creating a magnetic field. We've calculated magnetic fields tonight for a circular current loops, for square current loops, for rectangular current loops. This would be the magnetic field that you would create with a rectangular current loop, for example. But if you put in a chunk of magnesium in the center of that current loop, you will actually increase. It's a very small amount. That chi for magnesium, for instance, is equal to 1.2 times 10 to the minus 5, and it's dimensionless. But the total that you get, the total magnetic field will be chi plus 1 times the external magnetic field. I don't know if that made any sense, but see this, you get a small increase, an additional magnetic field because you have a paramagnetic substance. Not all materials are paramagnetic, but there's quite a few. But the total magnetic field will be a little bit bigger because the magnetic fields line up. It's like instead of the frog having opposing magnetic fields, it would have the north-south going, increasing the magnetic field of the external magnetic field. And finally, there's a third type called ferromagnetic materials. And that includes things like iron, nickel, cobalt, and those also have a chi, but they're very large. They can be hundreds. They can be anywhere from 100 to 1,000. If you put a ferromagnetic material inside I think I was telling you about that last time. You can just take a nail and wrap a coil around it, connect it to a battery, and the coil itself is like a solenoid, and you know the magnetic field of a solenoid is mu sub O Ni. But see, when you put a ferromagnetic material in there, like iron, nails made out of iron, it can multiply it by a factor of maybe 300 or so. Now that I've told you again a little bit more about the three types of magnetic materials, we're going to do problem 1259. So here goes. Let me find it. Let me find 1259. Here it is. A solenoid has a ferromagnetic core with 1,000 turns per meter. Okay, let me write this down. Now here's your magnetic field of your solenoid. We know what mu sub O is. We all know what that is. Well, I'll write it. It's 4 pi times 10 to the minus 7 Tesla meters per amp. They give us N. The N is 1,000 turns per meter. Turns are dimensionless, but meters aren't. Meters have dimensions. And the current is 5 amps. So we know all three of these, and we can get the magnetic field. If B inside the solenoid is 2 Teslas, what is the susceptibility for the core material? Okay, well, let's see if I can write that. Just need some room here. We'll get rid of this frog. They gave us B. They said B was 2 Teslas. So 2 Teslas is equal to 4 pi 10 to the minus 7 times 1,000 times I. Now what's I? 5 amps. But see, you're going to have to multiply all this by this chi plus 1. Here's your equation. Shame on me for not putting in units. Well, I put the units in on the Teslas, but we're going to solve this, and we're going to get the susceptibility of that ferromagnetic material. And it'll be big. It'll be bigger than 100, I bet. Stick all this in your calculators with me, and tell me what you get for this small Greek letter chi, C-H-I. Go for it. Plug all that in. Let's see what we get. Well, I got an answer. Well, what'd you guys get? Now, let me pick on somebody here. Let's go to my friend Nicholas. Unmute Nicholas and tell us what you got for this thing called susceptibility.
317.309886.
That's what I got. Now was that Nicholas?
Yeah.
Okay, Nicholas. It's dimensionless. And what that means is it's kind of like this nail. You put a nail in there in that solenoid, and you'll create a magnetic field that's 317.3 times the solenoid's magnetic field. Now to get the total, you'd have to add the solenoid to it. You see, what I got was 318.3, and then you had to subtract 1. Maybe that makes sense, but I think that's it, guys. Let's look at our answer here. This was 1259, and the answer is 317.3. We did great. I guess the thing I want you to remember is that if you have a ferromagnetic material we're not going to go into why they increase the magnetic field that much, but they do. Now, paramagnetic materials increase the magnetic field a little bit, but it's just very small. Very, very small. But ferromagnetic materials, man, that's a big increase. 317.3 times the external magnetic field. So we had a little bit there on your magnetic materials. Now the last topic for tonight is torque. We're going to study torque now. And I need the space here. Is there any comments or questions on anything before we go into it? We've studied it before. We've done it in lab even.
Yeah, I had a question. I thought I was listening, but so you were saying that on diamagnetic fields line up, but on paramagnetic, do they add or do they oppose? I'm a little confused.
Diamagnetic oppose, paramagnetic line up and increase your magnetic field. They're like the ferromagnetic materials. Ferromagnetic and paramagnetic both increase your magnetic field.
Okay, I think I got it.
See, you can even, there's a magnetic field of the earth. You all know that. You know compasses point north. Did you know that you can take a needle, just set it on your table, pointing north. There's your needle. There's a little eye there. Leave it there for a few days or weeks. It will become magnetized by the Earth's magnetic field. Now, if you turn the needle around and point it the other way, it'll become magnetized oppositely, obviously. Isn't that interesting? And you can create a permanent magnet that way. Now, another way of creating it is you can just take a nice strong kitchen magnet, north-south, and just kind of stroke this needle with that North Pole, and you can create a permanent magnet out of your needle. That's interesting. Well, let's talk about torque now. Unless somebody has another comment or question. We've talked about torque before. We had an experiment that we did where we had the sum of the torques was 0. We had a magnetic force times, well, it was 10 centimeters, equals to a hanger weight. And here we plugged in 0.01 meters, 0.02 meters, all the way up to, you guys remember that experiment? We put different hangers there and we found our magnetic force. Well, that's torque, see? Torque is force times the distance. We had this this magnetic field here. This is a North Pole, and this thing would want to go down. But we had a weight here, like at 0.5 in the middle here. If you put your hanger right there, that will want it to go to the right or clockwise. But this here will try to make it go counterclockwise. So see, if this was 0.05 and you knew the mass of the hanger times gravity, you could get the magnetic force. We did that. I don't know if you remember, but we did that. So we know what torque is, but what we're talking about right now is the torque acting on a current loop. Let's have our current loop again. Didn't we have a current loop that was, I forgot what the dimensions were. Oh, well, it doesn't matter. We'll just measure it. That's, it looks like 8 centimeters there. 0.08 meters. Everything would be 0.08 meters. It's a square current loop. And what we're going to do is we're going to have a magnetic field. We could just make up something. It doesn't matter. How about 8 Teslas? There we go. We got 8 Teslas. Magnetic field. 8 Tesla magnetic field. And now here's what's going to happen. There won't be any force on this bottom or top wire because, do you remember F equals IL cross B? Which is equal to ILB, sine of the angle between the L and the B. Now on this bottom wire, we got to have a current here or nothing's going to happen. Let's say the current's going this way. Got a current loop. We have our old buddy, the 10 amps. There we go. This would be the sine of, for this wire here, it'd be the sine of 180. Because our L vector, it's the length of our wire in the direction of our current, 10 amps. It's got 180. Well, sine of 180 is 0. This wire here doesn't give you any force. There's no force on that wire. And there's no force on this wire either. Because on that wire, what you have is ILB sine of 0. Because see, the L on this wire, the L vector is in the same direction as your magnetic field. But you do have a force acting on these 2 wires here. Now, we've studied this before, but it's just worth going over again. This is the principle of the motor. This is how motors work. Now here you got to go L cross B. Now L is going up on this wire here, and B is going over. Now if you cross those, what you'll get, right-hand rule, you'll get a force going into the board. There's a force going into the board on this wire. Now, if you cross these, our L is going to the left on this one, see? And so on this one, F equals ILB, IL cross B. The L is going this way, and the B is going, I did the wrong one, I'm sorry. We need to do this one. The L is going down, and the B is going to the right. And when you cross those, what you get is a force coming out. Why did I do that? It's this force on this wire that's going into the board, and the force on this wire is coming out of the board. And so what happens is this thing spins. If it was on an axis, it would spin. It would spin. I know, kind of hard to draw, but it would spin. Now the way you could depict that spin would be with a torque going like that. Now let's figure what that torque would be. You all know that torque is a force times a distance. And here's your distance about your axis. And it's, well, it's this length divided by 2. What would that be, 0.04 meters? Now the force would be ILB. The I is 10 amps. The L is 0.08 meters. And the B is 8 Teslas. But that's the torque on this wire coming out of the board. It gives you a spin. But if you want the total torque, you'd have to add them up. So you're going to have the same amount on this one. So the torque on that one is the same. It's whatever that is, 0.04 times 10 times 0.08 times 8. Let me see what that is. Let me get my calculator and see what that is. 0.04. There's an easier way. We're going to do it in an easier way here in just a minute. I'm getting this here is 0.256 Newton meters. And of course, this would be the same, 0.256 Newton meters. So your total, the total torque on a loop like that would be, you just add them up. Be 0.512 Newton meters. Now there's a much easier way of doing this, and that's with this equation here. Where this thing here is called the magnetic dipole moment, and it's equal to IA. Now if you have more than one loop, you have to multiply it by N. So it'd be NIA times B. We just have one loop here. And you should get the same answer. Let's try it. The I is 10 amps. This area is 0.08 meters squared. They call that the magnetic dipole moment. That's a fancy name for it. And B was the 8 Teslas. Now, if you multiply all that, you should get this same answer. Let's try it. Take, we're not going to get the same answer. I did something wrong. In just a minute now. No, I bet you do. I bet you do get the same answer. 10 times 0.08 squared times 8. Point you get 0.512 Newton meters, the same answer that you get this way here. We are looking at the torque on a current loop. Let's go over it again. I know it's a little confusing, but it's in your chapter. Let me show you where it is. See, the thing is, every atom, even electrons, every molecule has what they call a magnetic dipole moment. Can't find it. You know what? I think it's in chapter 11. That's why I was having trouble finding it. We're going to go back to chapter 11, and we're going to find the torque on a current loop. There it is. It's on page 517. Here, let me kind of go through it again with you. The topic right now is the torque on a current loop. And the equation for it is tall equals mu cross B. This mu is not, it's not mu sub 0. Mu sub 0, remember, is our old friend 4 pi times 10 to the minus 7 Tesla meters per amp. This mu here is a vector. You know what? This mu sub 0 is not a vector. But this one is. It's called the magnetic dipole moment. And every atom, every bit of matter has a magnetic dipole moment, because matter has charges that are either spinning or going around in an orbit, which creates this magnetic dipole moment. And now it's equal to NIA, where N is the number of, I guess, molecules or atoms or electrons, or for a current loop, it's the number of loops. I is the current around your loop, and A is the area of your loop. So the units for this are amp meters squared. That's a different kind of unit than that. And this is a vector. This is not. This is a scalar. It does not have direction. But this is a vector. It has direction. Now, the direction it has, it's perpendicular to the area involved. For instance, if you had that loop that we had a minute ago, what did I say it was? 0.08 meters by 0.08 meters square. And we just had one loop. So this would be 1 times the current, I think it was 10 amps, times the area, which would, in this case, it would be 0.08 meters squared. So you get amp meters squared, and I don't know what that is, but you could figure it out. And it's a vector, it's perpendicular to the area, and it's given by the right-hand rule. Now, if the current is going counterclockwise like this, if the current's going around and around counterclockwise, then your dipole moment is coming out of the board. It goes in the direction that a right-hand screw goes. If you have a right-hand screw, and you put your screwdriver on it and turn it counterclockwise, it comes out. If you turn it clockwise, it goes in. So this vector here is coming out of the board at 90 degrees. That's your area vector. Let's work some problems in that. And then maybe it'll make some more sense. Now, here's one here. This one's problem 1141. Do we have any questions before we work 1141?
Yeah, was it the magnetic dipole that's out of the board, or is it the area that's out of the board?
The magnetic dipole, that's a very intelligent question. The magnetic dipole is equal to, it's equal to NIA. And N doesn't have a direction. I doesn't have, well, current is a scalar.
Mm-hmm.
But the A does. And
Right.
in the direction of that area is perpendicular to the area itself and given by the way a right-hand screw would move. So the answer to your question is, say your question again. It was a good question.
Okay, so I'm really confused now. So there's area
Yeah,
and there's the direction the area is moving in.
right.
Then there is magnetic dipole, and I thought
Yeah.
they were perpendicular to each other.
The the magnetic dipole moment is in the
Yes.
same direction as the area vector. But see, the area vector is perpendicular to the area itself. See, area itself doesn't have any direction.
Okay.
Here, let's work a few problems and then
I got
maybe.
it now.
Yeah, okay, great. This is going back to chapter 11, and we're going to work problem 1141. Here goes. It's important because it's the principle by how motors work. They turn because there's torque on them, and the torque is caused by this equation here. This is the equation, and these are all vectors. Okay, in 1141, let me find it here. Here we go. Let me dig around and find it. All right. 1141. Find the current through a loop needed to create a maximum torque of 9 Newton meters. Okay, well, let me write that down. They said the torque is 9 Newton meters. The loop has 50 square turns that are 15 centimeters on a side. Well, let me draw that. It's square. They're 15 centimeters on a side, so that's 0.15 meters. 0.15 meters. And how many turns are there? 50. This goes around 50 times. N is equal to 50. That's just the turns. It doesn't have any units. Now the area will be 0.15 meters squared. That's the area that we're talking about. But see, depending on which way the current's going, if the current's going clockwise, then the area vector is actually going into the board. If it's going clockwise. If it's going the other way, counterclockwise, the area vector would be coming out of the board. Now let me read some more here. We're doing 1141. Okay, and we are in a 0.8 Tesla magnetic field. All right, but we don't know the direction on it. All we know is the amount. We know this. And I think we know this. In fact, I think we know, don't we all know all three? Just a minute, I'm getting mixed up here. Oh, no, we don't know the current. I take that back. We don't know the current. But we do know that this is 9 Newton meters. And we do know this is equal to the 50 turns times the current times the area, which is 0.15 meters squared. I just about goofed up. You don't want to put the 2 there. You want to put it outside the parentheses. And then the B, we know what the B is. It's 0.8 Teslas. Now, if you want the maximum, you need to sign a 90. which is 1. Hey, we got it made here. All we got to do is plug this in and solve for I, and we'll talk about it. I'll shut up. I want you to find that current, and then we'll talk about it. Go for it. Well, I think I know what the current is. Let me go to one of my students here. How about, let me pick on Phoebe again. She's a good sport. Phoebe,
Yes,
what'd you get for the current?
10 amps.
That's what I got. You know, they were a little bit vague about which way the current was going. So let's just make up what might work. Suppose that this is your square current loop with 50 turns. And there's the dimensions. It's square, 0.15 meters. And let's put the magnetic field going this way. Okay, so here's our equation. The torque is going to equal mu cross B. And like Phoebe was telling us earlier, this mu has got to be in the same direction as your area vector. Now the area vector is going to be going into the board. That's the direction of your area vector. It's into the board. And B, we know, is going this way. Now when you cross into the board with B, I get a torque going down. How about you? So this thing will spin. It'll spin about its axis this way. The torque is going down. I often put a double arrow on my torques to make sure that they're not forces. See, a single arrowhead is a force, but a double arrowhead is a torque. See, forces are in newtons, but torques are in Newton meters. So what that means is this thing's going to spin around, kind of hard for me to draw, but it's going to spin around that way. Again, if you take a right-hand screw and turn it clockwise like this, it will go down. So see how I'm turning this screw? When you turn it that way, it goes down. Now the numbers, let's put in the numbers. This number is 9. This number is 50 times 10 times 0.15 squared. Let me get that number. See, this mu here is 50. Mu is equal to NIA. So you go 50 times 10 times 0.15 squared. This is 11.25 amp meters squared. And the B, they gave it to us, it's 0.8 Teslas. Now, if you take 11.25 times 0.8, you should get 9. Try it. By Jove, it works. Now let's look at our directions. Well, we already did that. You go into the board, you turn it into that B, and it will go down. So there's an example there. maybe we could do another one. Okay. All right, let's do this one. Well, no, wait a minute. That doesn't have answers in the back. I like them when they have answers in the back. Let's do 43. That'd be good for us. Do we have any questions on 1141?
I know that this is kind of dumb, but I still am confused on how you know which direction your torque's going based on the direction of your area and field.
Okay,
Because you
well,
were
here-
like, well, this
me show
goes
you.
in.
Now you understand that this mu is going into the board because that's the direction of your area vector. You
Yeah,
understand?
that part makes sense.
And B is going to the right. Now,
Yeah.
what would be simplest is just to use this IJK business, Phoebe. We were showing you this all one night. IJK, IJ. Now, when you go I cross J, you get K. When you go J cross K, you get I. When you go K cross I, you get J. Now, when you go this way, when you go J cross I, you get a negative K. When you go I cross K, you get a negative J. When you go K cross J, you get a negative I. It's always positive going on the top. And now let's see what this is. Now, you know our directions. This way is I. This is J. And K is coming out of the board. So this, you know what that is? That's a negative K, isn't it? And this is an I. And what you have is a K, a negative K cross I. Well, K cross I is J. So a negative K cross I would be a negative J. This should be negative J. Well, it is. See, J, positive J is going up, negative J is going down. Did that help any, Phoebe?
A little bit, yes. I do appreciate it.
Well,
I'm going to
that's-
have to review it some more on my own, but I do think that helps. Thank you.
Yeah, that's one way of looking at it. I don't even look at it that way. I look at it with the right-hand rule. See, I've got something going into the board here and something going to the right. I don't know if you can see this very good, but this is going to the right. This is going into the board. And what I'm going to do is I'm going to turn that into that. And when you turn something like that into that, it's like a right-hand screw that you're screwing in, it goes down. That's how come it goes down. That's how come the torque is going down. Well, let's do another problem. We got time. Here we go. Let me make some room here. Now read your lab description for Thursday night. We could talk about that, but I'll talk about it Thursday night. You guys seem to enjoy lab. Okay, now this is 1143. It's back in chapter 11, but I just think we needed this. This is just dimensional analysis. Let's see if we can do this. We have this lovely equation here. We know it goes like this, only they decided to write it like this. They just wrote the scalar amounts. And we're going to put in the units and make sure the units work. Now, torque is always Newton times meters. The number of turns is dimensionless. Current is in amps. You see where you could get confused? You see that A there? That's not amps. You see that A there? That's amps. That A stands for area. In fact, the units for that is meters squared. B is Teslas. And did you know the sine of theta is dimensionless? The sine of angles is dimensionless. Well, somehow we've got to show that an amp meter squared times a Tesla is a Newton meter. Well, we can do that. A Tesla is equal to a Newton per amp meter. So if you stick that in here, you have an amp meter squared Newton per amp meter. Well, looky here, the amps cancel, one of the meters cancel, and you're left with newtons times meters on the right, Newton times meters on the left. And boy, Jove, we've done 1143. Any comments on that? Well, let's do 45. We got time for one more problem. This is 1145. I bet we can do it. Any comments or questions on anything? All right. We're looking at 1145. Now they're talking about a proton. It has a magnetic field due to its spin. Did you know protons spin? The field is similar to that created by a circular current loop whose radius is 0.65 times 10 to the minus 15. Well, here, let me draw it for you. We've got a circular current loop, and the radius of this current loop is 0.65 times, we're talking about a proton now. It's pretty small, you know it? That's the radius of our proton. But now there's a current going around here. I don't know which way it's going. I'll just fake it and say that it's going around like that, of 1.05 times 10 to the minus 10 to the 4 amps. Man, that is a lot of current, you know it? I'm kind of concerned about that. Find the maximum torque on a proton in a 2.5 Tesla field. Okay. I'm a little bit confused about the amount of that current. That is a heck of a lot of current. But it's going really fast. These little molecules zip along pretty fast. Did you know that the electrons in a color TV, back in the old style color TV before they had these flat screens, was about 1/10 of the speed of light? That's pretty dang fast, folks. 3 times 10 to the 7th meters per second. I don't know whether to believe that current, but we're going to go with it. They do spin around fast. Okay, we have the current, and the N is equal to 1. We're just talking about one loop. We have the radius, and we have the field. Now, the field, we could just say this is your field here. Do they tell us what? 2.5 Teslas. Here we go. 2.5 Tesla field. Now the torque, is that what we're supposed to find? Yeah, find the maximum torque. Okay. Well, we've got the equation. I think we can get this mu thing. It's NIA. Its N is 1. I is 105 times 10 to the 4th amps. Gosh, that seems awfully big, but I'm just doing what the book says right now. In IA. Now the area, we know what the area is of a circle. It's pi r squared, right? So it's pi times 0.65, 10 to the minus 15 meters, pi r squared. There you go. Times B. Uh-oh, running out of room here. 2.5 Teslas. Well, that's it, guys. This should be the torque. It should be, if you multiply all this stuff, go ahead and get it for me. Plug all that in and let's see if we can agree on this. We got 3 minutes left in class. We can do this. Well, I'm getting a very, very teeny tiny amount of torque. When you draw your little tall, take a pi, you know what pi looks like, kind of like that, and just knock one of the legs off. There you go. Now you got your tall. There it is. Okay, I did this. Did anybody get 3.48 times 10 to the minus 26 Newton meters? Anybody? If so, say uh-huh.
Uh-huh.
Okay, well, let's look up the answer. This was 1145. I'm curious to see if we got what they got. 1145. They said 3.48 times 10 to the minus 26. This is what the book says. Newton meters. Boy, Juve, we got what the book got. Yay! Well, we've had some fun tonight, and we've talked about magnetic fields, toroids, torques. And I want you to get your lab description and study that. And it's another lab on the RC time constant. Now be careful, that's tau equals RC, but that's not a vector. You see this tau here? That's a vector, that's torque. This here is in seconds. Torque is in Newton meters. Do not get confused. Okay, here's your last chance to say anything, because I'm going to put this cursor over this red box. Last chance to say anything. Well, okay, I will see you Thursday night, and we'll have a good time in lab. Do your homework. Bye-bye, students.
Bye.
Bye.